Welcome back, students. In this video, we are going to look at arrow pushing patterns for reactions. Do you remember when you were in general chemistry and you talked about metathesis or double replacement reactions, and you had to predict the products for those reactions? Well, that's essentially what we're going to be doing for the rest of the semester. We are going to look at different reactions and predict each reaction's products. The problem is there's going to be a boatload more reactions than you saw in general chemistry. What we need to do to be successful then is to start looking for patterns, because if we don't find patterns, it's going to feel like you are looking at 50,000, it's not 50,000, but it's going to feel that way, different reactions. Let's start by looking at what I have written in the middle of my page here. Here I have what's called a mechanism. In a mechanism, what is happening is we are using curved arrows to illustrate the flow of electrons and how bonds are forming and breaking in order to form a final product. This is going to help us predict products in the grand scheme of things, but right now it's just going to feel kind of overwhelming. There are four main patterns that show up in our mechanisms that we're going to look at. This set of examples, this only has a couple of the patterns that I've listed below. I want to look at each individual pattern as we move forward. So let's start by looking at something called nucleophilic attack. When we look at nucleophiles, they attack electrophiles. What happens is the nucleophile has an excess of electron density, and we're going to draw a curved arrow that shows where the electrons on the nucleophile are going to attack on the electrophile. So I'm going to point my arrowhead to the atom that is the electrophilic atom in my structure. It's, in this case, the carbon that bears the positive charge. The key here is when you're looking at nucleophilic attack, your electron pair is where your arrow tail must start. The most common wrong thing with arrows is putting them in the wrong location at the start, and this is a personal pet peeve of mine. A lot of times what will happen is people will start their arrow at a charge. And a charge is not a physical entity. You may not start an arrow tail at a charge, because a charge is a discrepancy between the number of protons and the number of electrons for a particular atom. It is not a pair of electrons that is capable of making a bond. So when we draw our arrows, if we're starting like with nucleophilic attack, where we're trying to say this lone pair on bromine is going to form a bond with this carbon, then we start our arrow tail at a pair of electrons and we point that arrowhead to the carbon that bears the positive charge. We're not pointing it to the positive charge. We're pointing it to the carbon that has the positive charge. And with time and practice, what you'll end up doing after you've identified these patterns is you'll also be able to draw what the product is after you have seen these patterns. And so we'll work on that when the time is right. In this particular arrow pushing pattern, we are creating a new bond. We are creating a bond between bromine and the carbon that bears the positive charge. Let's look at another format for nucleophilic attack. In nucleophilic attack, your nucleophile is still going to attack your electrophile, but this one's a little bit different. The reason that this one's a little bit different is the electrophile that we are attacking is this carbon that I've just highlighted in yellow, and there's already 4 bonds there. Now, if there's already 4 bonds there, the problem is going to be when a lone pair from my nucleophile attacks my electrophile, this arrow that I've just drawn is saying form new bond. But you already have 4. What are you going to do? Well, you can't have 5, but the reason it's going to work is because you have a carbon-oxygen double bond, so this pair of electrons that makes up that pi bond can go on to the oxygen as a lone pair. And oxygen can accept that excess electron density because oxygen's electronegative, and so it's perfectly capable of doing that. You're probably looking at this example and saying, how did she know that the lone pair on the alcohol was going to be the nucleophile instead of the lone pair on the ketone, the C double bond O? The answer to that is lots of practice, and also the other way wouldn't make sense. You could always try it. You could start your arrow at this pair of electrons and point to somewhere on that other structure. And if you point to, say, this carbon, it's not going to work because then you would make 5 bonds. The reason that we could point to form a new bond to our carbon that's highlighted in yellow is because there was a pi bond there that could be broken. Right? That's why that one worked. So the answer to your question, you're not going to appreciate of how did I know, because I have lots of practice, and eventually you're going to have lots of practice and you won't be so freaked out. So right now, what we want to do is just classify patterns so that when we start to see actual reactions, we can make better sense of them. Our next pattern is called the loss of a leaving group. Let's talk about what a leaving group is really quick. A leaving group is a group on a compound that leaves during the course of a reaction. Very aptly named. And sometimes the nucleophile forces out that leaving group. And this is one of those examples where the sulfur is my nucleophile. It's going to go ahead and it's going to attack the carbon that has the leaving group attached. That bromine is my leaving group attached, and how do I know that that's my leaving group? Well, leaving groups need to be stable when they leave. They need to be things that can take on excess electron density. And another way you could think about it as leaving groups are essentially weak bases. Right? Once they've gone and they've separated from the rest of the molecule, they're pretty satisfied just hanging out right there. Eventually, when the time is right, we will end up making a list of the good leaving groups that you're going to typically see during the course of our reactions. So again, your nucleophile in this case attacked your electrophile and it forced out the leaving group. The leaving group has to be able to take on excess electron density. This isn't the only way a leaving group can leave. Sometimes the leaving group can actually just leave all on its own. And if the leaving group just leaves all on its own without something forcing it out, the reason that it can do that is that whatever the result is after that leaving group leaves is pretty stable. And in this case, if that bromine were to leave on its own, I'm actually going to draw the products for this one. What would happen is now you would have a carbon here with one less bond, and then you'd have bromide ion floating around in solution. The carbocation is stable, right? The leaving group is stable, bromide ion is a weak base, and the carbocation is stable. How do I know the carbocation is stable? Well, I can draw resonance structures for it. Oh man, resonance? You mean I have to remember resonance? Yep, yeah, that's never going away. So I can absolutely draw resonance structures for this, which makes this a nice stable carbocation. So your leaving group can either be forced off, like we saw in the last slide, or your leaving group can leave on its own. Either way, the leaving group needs to be stable once it's gone. The next set of arrows that we're going to look at are called proton transfers. You've actually already seen proton transfers before. You've seen them when we looked at acids and bases. Let me just draw a couple of proton transfers with you. So for this first one, I have an acidic proton here, and water's one of those fancy molecules that can behave as an acid or a base. And so water's just going to come in and it's going to pull off a proton here. If you're looking at that going, why? Okay, then you need to go back and talk about pKa's. Then for the next one, it's just going to be the opposite. You have an acid, and your oxygen that has a pair of electrons is going to come in and it's going to pull off a proton. This final one is one of my favorites because it doesn't look like it should happen, but this hydrogen down here at the bottom has a pretty low pKa. It has a pKa of 9, which means that hydroxide ion is actually a strong enough base to come in and pull off that proton. When hydroxide pulls off that proton, these electrons right here are going to hang out on that carbon between the two C double bond O's. Those C double bond O's have a name, by the way. They're called carbonyl groups. And so you have a carbonyl, a lone pair, and a carbonyl, and that you can draw resonance structures for as well. Here is a wrong way to draw a proton transfer. When you draw a proton transfer, you always have to have a base pull off or abstract, right? Abstract is the fancy chemistry word for abstract that proton. This drawing that I've drawn here is one of my ultimate pet peeves that even shows up in textbooks. This is not how arrow pushing works. This is not math class, okay? We don't get to say, hey, see this proton right here? We want to get rid of it, so we're going to subtract it away like you do in math. No, 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 no. No, there's no fancy wand waving over here in mechanisms, right? Mechanisms are the curved arrows. What happens is that a base is going to come in, and B is just going to be my general base. And the base is going to pull off that proton in order to get that ketone as your product. So no fanciful subtraction of hydrogens. If you see that in a resource outside of your class, run away. Just don't use it. They're probably making other mistakes with arrow pushing. And if you're my student, I expect good, correct, non-ambiguous arrows and no magic. Here's our last type of arrow pushing patterns, and it's called a rearrangements. Rearrangements happen with carbocations. When we have a carbocation intermediate, carbocations can often rearrange to form a more stable carbocation. And I'm going to show you one, and then we're going to talk a little bit about stability, and then we'll go back to some more examples. So here I have a carbon that is positive, and this is called a secondary carbocation. The reason it is secondary is because the carbon that I have highlighted has 2 carbon groups attached. And what can happen is a hydrogen can shift over, so the hydrogen plus its electrons, which is technically called a hydride, can shift over one location. And when that happens, now your hydrogen is here, and we've left a hole over here. If we focus in on our new location of our carbocation, we have 1, 2, 3 carbon groups now attached to that position. So we've gone from something called a secondary carbocation to something called a tertiary carbocation. This is called a hydride shift. It is a form of rearrangement that happens when you can create a more stable carbocation. And you should be thinking right now, but how do I know which one's more stable? Let's talk about that. When we look at carbocations, we have to know which ones are more stable in order to decide if a rearrangement happens. Carbocation rearrangements is like water flowing downhill. You can't stop it. It's going to happen. You just need to notice when it's going to happen. So if you had something that was a tertiary carbocation, it wouldn't become less stable, right? Things only become more stable when we're talking carbocation rearrangements. Let's look at carbocation classification and stability. Here I've drawn all of these carbocations in their Lewis structure format instead of skeletal notation. So I can highlight the carbon that bears the positive charge. When you have a carbon that has 3 hydrogens attached, that is called a methyl carbocation. When you have a carbon that's positive with just 1 alkyl group attached, remember R is an alkyl group, so any carbon group here, this is called a primary carbocation. Then if we look at the next one, we have 1 and 2 carbon groups attached, so this is called a secondary carbocation. Our next one has 3 carbon groups attached, and so this one is called tertiary. We can also abbreviate primary, secondary, and tertiary. People will call this 1 with a dot, 2 with a dot, and 3 with a dot. So we can classify these as primary, secondary, and tertiary more quickly. When we're looking at stability, stability increases going this way. So this is your most stable, and your methyl is your least stable. Your methyl and your primary carbocations, if they're not involved in resonance, and the methyl would never be, are not going to form. These are not stable enough to even form, so these are very unstable. But your secondary carbocations can form, your tertiary can form, and then in addition to this, things that are resonance stabilized can form, even if they're primary. So if we're looking at something that's involved in resonance, like an allylic carbocation or a benzylic carbocation, those are also going to be on the more stable side. So we'll just add allylic and benzylic here. Do not be afraid to Google what those words are if you need to. I remember being a student and being like, what does allylic mean? It takes a long time for all those words to sink into your brain. Now let's look at the two forms of carbocation rearrangement. The first one is hydride shift. We already looked at it for a moment, but let's look at it again. This is what you're going to do. Keep in mind that you are just trying to predict on paper whether or not a shift will happen. You don't get to decide whether or not the shift happens because the molecule is already saying, hey, I'm going to the more stable state. So we're just trying to give our guess as to if a shift is going to happen or not, and it will if you have a more stable carbocation that can form. What I want you to do is find the carbon that has the positive charge on it. Once you find the carbon that has the positive charge, look one carbon away. So this carbon and this carbon. These are the locations that you can have a shift happen to, right? So at the end where your positive charge can be. Look at those locations and decide, if my carbocation shifts to one of those positions, does it become more stable, yes or no? Right now, this is a secondary carbocation. I know it's secondary because I found my carbon that bears the positive charge. I looked here and here. There are two carbon groups attached. That makes this secondary. Now, in my brain, what's happening off to the side is I'm assessing, what if my positive charge ended up here? And what if my positive charge ended up here as one of those more stable than my current secondary? Well, this one, where the positive charge is still secondary because you have two carbon groups. So that's still secondary. Secondary is not going to shift to secondary if there's no resonance involved. Now I look at my other example. I have my positive charge here, and I have 1, 2, 3 carbon groups, which makes this tertiary. Secondary will shift to tertiary. So now that I've worked on that in my brain and I know where I want the positive charge to end up being, the question is, how the heck do I get it there on paper? What will happen with hydride shifts is we will draw in the hydrogen, because a lot of times we're in skeletal notation and the hydrogens aren't drawn in because they're assumed. And we're going to draw in that shift that happens between the hydrogen and the pair of electrons over one carbon, right? And I know I'm crossing over like a line, that doesn't matter. All that matters is that only an adjacent atom can do that shifting. So you can't like hop multiple times, right? It's not like a bunny. There's no Easter bunny in here that's like, hey, 5 steps down the path, I see a more stable carbocation. No, that's not a thing. So the hydrogen plus its electrons can move one carbon over. And it's called a hydride because hydride is the name of a hydrogen plus its pair of electrons. So we can draw the product at the end where this part didn't change. Now your hydrogen is at this position, which left a positive charge here. Now there's one other type of shift that can happen. It's called a methyl shift. And a methyl shift will happen only if a hydride shift is not possible. In this example, what I see right away is I have a carbon that is secondary, and then I just got this boatload of carbon off to the side over there, and my brain is like, I want the positive to be on that carbon that I highlighted in blue because I know that's going to be more stable. But then I look at it and I think, wait, there's no hydrogen to shift, right? There's a methyl here and here and here. Remember, methyl abbreviation is Me, right? Those are all methyls. So in this case, the methyl is going to shift. What we would do is we draw the line from just one of the methyls. They're all the same in this case, so it doesn't matter which one we use. So we start at the middle of the bond and we point to the carbon where the positive charge is. Right, so we're taking the methyl, the CH3 plus its electrons, and we're putting it in a new location. And the new location is here. And it might look a little bit different, my drawing, because I just naturally spread out my bonds. Now that methyl is on this carbon, and the carbon that I highlighted in blue is still the same highlight. I'm keeping my highlighting so you can see which carbon is which. And now that there is one less methyl here, there's a positive charge. So we've went from something that is secondary to something that is tertiary. You might be looking at this and thinking, why didn't we talk about this position at all? Because if we were to put the positive charge on that position through a hydride shift, you'd end up with a primary carbocation, and that's flowing uphill, right? You're going from secondary, which is moderately stable, to primary, which is unstable. That's not going to happen. So I didn't even consider the other side of that molecule. Let's do a quick summary about curved arrows. When we are drawing our curved arrows, make sure your arrow tail is always starting at a bond or a lone pair. If it's starting at a lone pair, just pick one and make sure your arrow tail starts there. If you're starting at a bond, like if we're going to do something like this, start your arrow tail at the middle of a bond. Where your arrowhead points is going to show the formation of a new bond or a lone pair. So if I want to point to this carbon, that's saying form a bond to that carbon. If we go back to the example I just drew above, this one is saying where I point my arrowhead, put a lone pair there. Remember that we cannot violate the octet rule for carbon, nitrogen, oxygen, or fluorine, right? These can only have 8 electrons around them, no more than that. Let's wrap up. In this video, we looked at the 4 main patterns for mechanistic arrows. We looked at nucleophilic attack, loss of leaving group, proton transfer, and rearrangements. Make sure you're really particular with your arrows because I am, and I expect you to be. Thanks so much for watching. This is Katoni, signing out.